So this video is going to be helping you see if molecules themselves are polar. Now you already watched the video to determine if bonds are polar, but here's the thing. A molecule, like H2O for example, has two different bonds, this bond and this bond. Each of these bonds may or may not be polar, and what we're going to consider is whether the molecule as a whole is polar or not. If a molecule is to be polar, it must meet two requirements. It must have polar bonds, and it must not be symmetrical. So let's kind of look at those things one at a time. Now H2O, indeed it does have polar bonds. I can tell by consulting a table of electronegativities like we did in the other video. I can also tell because oxygen is just really darn electronegative. It's the second most electronegative element. And in fact, the culprits you really want to look for polar bonds are our three or four most electronegative elements, those being nitrogen, oxygen, fluorine, the most electronegative element, and maybe chlorine too. If one of these guys is involved, unless they're bonded to themselves, probably you've got a polar bond going on. So H2O does indeed have polar bonds because this bond is polar and this bond is polar as well. So we meet that requirement. What also must be true is that the molecule must not be symmetrical. Now, when I say symmetrical, I mean where the atoms are related to other things, and if it's literally symmetrical. So this molecule is symmetrical in this plane, it's symmetrical this way, but it is not symmetrical this way. So what's going to happen is this oxygen, it's a very electronegative element. What it means to be electronegative is you pull electrons towards yourself. So this water molecule is going to be pulling electrons here towards the oxygen, pulling electrons in this direction. There's nothing to cancel that out or to pull the electrons in the opposite direction. So this molecule is indeed going to be polar. And when we're looking at H2O, since the electrons are being pulled here towards the oxygen, this is the negative end and this is the positive end. Now let's look at some more examples. Let's say F2. Let's say this represents F2. Well, this molecule is not going to be polar. It meets neither requirement, actually. It's symmetrical. It doesn't have polar bonds either, though. Fluorine's electronegativity is 4, and the other fluorine's also is 4, so when you subtract those, it's 0, so it doesn't even have polar bonds. So it doesn't meet either requirement. Let's look at another example, like let's say HCl. And again, these last two we've looked at have just been molecules with only one bond. But this stick, this represents a bond. The HCl bond is indeed polar. It's got one of my big culprits in there that's involved. I could also just use my electronegativity chart, like we did in the other video, and subtract them. But I do see that this is a polar covalent bond. The chlorine end is going to be partially negative because it's the more electronegative atom as opposed to the hydrogen end. So indeed HCl would be a polar molecule. Let's look at another example. Let's say yellow typically is used to represent hydrogen, but let's just say that this molecule represents CF4. And we'll pretend these yellow ones here stand for fluorine. Now, I'm going to move this up just a little bit. So this molecule has 4 bonds, 4 sticks, 4 bonds. Each one of these bonds has the potential to be polar. And if we check out the electronegativity values, indeed the carbon-fluorine bond is a polar bond. Fluorine's the most electronegative element. If it's involved in anything, you have a chance for that bond to be polar, and this bond is polar. However, what we're considering, though, is the molecule as a whole. And when we're looking at this, there's 4 fluorines, but they're all sort of equal and opposite from each other, and they're tugging electrons in totally equal and opposite ways. So this molecule is symmetrical. For a molecule to be polar, what you need for it to develop 2 ends that are distinct and different. So this molecule is not polar, and it's not polar due to the fact that it's symmetrical. Now if we change this up just a little bit, and swap out a couple of our pieces and parts. If you give me just a moment. What I'm going to do is I'm going to make a different molecule, like let's say that one. And let's say that that's CH3F. And these yellow ones will be the hydrogens, the F will be the fluorine. So this molecule is going to be polar. It's got a fluorine down here on one end. It's got nothing to cancel that out or pull electrons the other way. It's got these hydrogens, but hydrogens are much less electronegative than fluorine. So electrons are going to be pulled here down towards this end, to the fluorine end. So a molecule like this one, CH3F, it's polar. It has a polar bond. This bond is pretty polar. And it's also not symmetrical, so it meets both requirements. And that would be indeed a polar molecule. One more example. CO2. When you build a model for CO2, it ends up looking like this. Now, if we're going to decide if CO2 is going to be polar, it's got to meet both these requirements. It's got to have polar bonds, and it must not be symmetrical. It's got two bonding regions. It's really got 4 bonds, but either way, this carbon-oxygen bond here, it is polar. Oxygens are second most electronegative element. But then we've got a second carbon-oxygen bond, and that's polar as well. But the molecule as a whole is actually nonpolar, because it is symmetrical. It's symmetrical this way, it's also symmetrical this way. If a molecule is going to get polar, it has to develop ends that are different, like a magnet. This is not going to develop 2 distinct and different ends. Electrons are pulled this way towards one oxygen. That's what it means to be electronegative. You pull electrons towards yourself, but electrons will also be pulled towards this end. And almost as if we've got 2 totally equal teams playing tug of war, pulling this direction, overall we don't move, we don't go anywhere. Same thing with this here. We've got electrons being pulled in one direction, electrons being pulled in another direction. You can sort of just think of it like they totally cancel each other out. So CO2 ends up being totally nonpolar. Now I understand that polarity can indeed be a very confusing topic. Really the best way to figure it out is to actually build model kits, really look at them, think about the things I've said, think about the symmetrical issue, and if you build these model kits, if you work with them, if you think it through hard, hopefully you can get this figured out. Thank you, and good luck.